Good.
Okay, so welcome to Esri Portland, everybody. We're going to tell you a little bit about a project that we worked on called GeoBin, and it'll be kind of a little overview, and we'll tell you about some lessons that we learned along the way. I think we did the introductions, but Cortland Fowler, Josh Yaganay, Ryan Arana, Nate Goldman is not here. He did some magical front-end stuff that is well beyond my capacity. So GeoBin is like RequestBin, which is a website that lets you create a URL that you can post stuff to and watch it come in real time if you've got the web page open. So we made that, but with a map. So I'll do a really quick demo just to show you what it does. So this is GeoBin, and if I can find my mouse, you can create a new GeoBin, and it'll make you a nice little URL here that you can then post stuff to. Because this is a quick example, we'll just grab the little curl command that's there and paste it into Ryan's terminal. And then if we go back, you can see that we found some stuff on the map, and that's the request that we sent. So we made GeoBin because RequestBin is really cool, and we kept using it and thinking RequestBin is awesome, but it would be really great if we could actually see the geodata that we were sending to it. And then the real kicker is we work on a thing called the GeoTrigger service, which is a web service and mobile SDKs that allow you to create polygons on a map and specify messages to be sent to mobile devices when people walk into those polygons. One of the options is a callback URL on the triggers, and that thing, if you point it at GeoBin, you'll be able to visualize what's going on really easily. So with that, I'll hand it off to Ryan, and he'll do a real demo so that this hopefully makes a little more sense.
Yeah, so with the GeoTrigger service, we have a few tools, mainly the GeoTrigger editor, which, like he said, allows you to visually put a polygon on a map. And then we also have this faker. Both of these things, I should also mention, are open source and made by the amazing Nate Goldman. And anyways, the faker lets you pretend to be a device out in the world so that you don't have to actually walk out around and fire these things off, because while we liked all the exercise we got, it got a little cumbersome. But let's actually go do the demo. First, this is the page that you would log into if you were a user of the GeoTrigger service and the two tools that I just talked about. This is the editor, and I've already drawn a couple of triggers, one on the 9th carts here, and one on the office here. Here are our polygons. If we look in the list, we can see what is defined about these things. And basically, a device that has the following tags, test, when it enters the 9th location here, we will send it a message that says good eats, and we will notify a URL. And that URL is from a previous run, so I'm going to come over here and get the one that Josh created, which is right here. So I'm just going to grab this bin's URL and put that in here. And update it. So now the 9th carts, when we enter it, it will post this notification. It'll send it to the device, but it will also post the notification to GeoBin at that URL. So with the faker, we can set it up. I want to make this visible along with this so that we can see it come in real time, so that we can prove that we're using WebSockets. So over here, we'll initialize the device. So this is just creating a fake device in our system, and we're going to have to add the test tag to it. And once that's in there, then we'll send a fake location update that's outside of the trigger. And this is completely not related to GeoBin, but it's just showing the request and the data that it posted, and then the response that it got, which is a bunch of stuff that we don't really care about right now. But it so it will post to there, or we posted that location update, and then as soon as we post another location update that is inside this trigger, it sends another one, and boom, it magically pops up over here. And so now we can, let's turn that one off, zoom in on just that one, and make it big. And then zoom in on that one. So now we see both the trigger. We got a post from the GeoTrigger server that gave us the geometry of the GeoTrigger and the location update that fired it. And if we look here, we can see the details. We can see the exact raw request headers that were sent to us, the raw request body that was sent to us, and this is pretty large. We see the time that it fired. We see the trigger, and within that there's a condition and a geo, and that's where we finally get to some geodata there. And this in particular is just lat, long, and distance, and then there's a bunch of other stuff all about that trigger that we send over. But the other important thing in here is this location object, which shows the latitude, longitude, and accuracy. So that's all fine and good, but you can get all that from request bin. So the cool stuff is down here in the found geographic data. So in here, this shows the geographic data that we found, and it also shows that we converted it to GeoJSON. So we received the data that we received. Oh wait, I'm on the wrong one. So the data that we received was lat, long, accuracy, and then some other stuff. But the geodata that GeoBin gave us back is valid GeoJSON. Which, if you don't know what GeoJSON is, it's a JSON, an open spec for geographical data for serializing it to JSON, as you might be able to concur from the name. But we also add in this radius key because there isn't that in GeoJSON, and the path in the raw request data that was posted to us, the path to get to this data, which is how the map is able to show this on the callout, because it goes, oh, this location key is what I need to show. So then the more interesting one is the path trigger condition geo, and this one is able to show that as well. So that's the basic demo. So I'm going to talk about all the things that we found most interesting about how we built this, and basically that is the way that we parse the data, and then Court will talk about the WebSockets and how we use those, and the mocking Redis for tests, because testing is good. And then Josh will talk about the rate limiting middleware that we wrote. Since this is a free service, we needed to make sure that it didn't start costing us a lot of money. And a brief bit about our deployment process. So, parsing the data. We want to receive a post that looks like this and be able to pull some data out of it. And what this is highlighting is that we can take GeoJSON. If we receive GeoJSON, we'll just pull that out as it is and run with it. However, we will also take any, well, not any, but we've defined a few keys that we'll go looking for. And so something that looks like this will make it as well. And I'll get into that some more, but again, these are the keys that we go looking for each thing, and then we'll also take an array an array of numbers or floats that are in any keys that look like that. We will read in the order of X, Y, or longitude, latitude. So this is the ASCII art flow diagram of how this parsing works. First off, we check if it's GeoJSON. If it is, then save it. and the path that it took to get to it. If it's not, then we iterate through all of its keys and save any valid values for any of our geo keys. And then if any of the values are an object or an array, we go back to the beginning and recurse our way until we get all the way down to all the leaf nodes. Once we're done iterating through the keys, we check to make sure that we got at least an X and a Y, and if we did, then we add it to the found geo set and carry on. Otherwise, we don't. So that was the basic overview, but the minutia details of how we did this, as I was saying, we do it all concurrently. And so the first thing we thought to do was put some channels on it. And so we had this GeoBin request object that got created with every request that we received, and that object had a wait group and a channel. And we would then fire up a go routine that listens on that channel, and any geo that was passed into it or came out of it would then be added to an in-memory slice, and we fire up a bunch of go routines that were doing this all at once. And that was because the parse method then goes through and recursively calls itself, searching for this geodata and sending any that it finds into the channel. And so we thought that that would work, and it ended up causing us a lot of race conditions and go routines sticking around forever because we couldn't track when to close the channel correctly. And we just ended up being a lot more complicated than just doing a mutex. And so we abandoned it and put a mutex on it. And so then our GeoBin request object had a mutex, and it still had the wait group. And then the parse method just adds one to the wait group, fires up a go routine, and parses the object that it's given. But as it takes that object, it fires its way down to the leaf nodes, recursively calling itself and searching for geodata. But this time, when it gets geodata, it just calls a method that sets the lock, writes to the slice, and then unlocks. Just standard mutex stuff. So the lesson learned there was not to let the channel hammer make all of your concurrency problems with nails. And so now we're going to talk about WebSockets.
Yay, WebSockets, right? Everybody loves WebSockets. If you don't know what WebSockets are, you might not love them, I suppose. So just really briefly, a WebSocket is a communication protocol over TCP. It has sort of bidirectional communication simultaneously. Typically, this is being used in web apps to kind of do what we were showing you, like real-time response from the server when things happen. Basically, what that looks like is the client makes a request to the server. There's a route for that, just like any other request. The server gets that request, upgrades the HTTP protocol to the WebSocket protocol, and then you're on your way. It's pretty straightforward, and there's libraries that do all the hard things for you for the most part. This is the library we're using. It's the Gorilla library, which is a very good library. I think there's at least one more that I know of, but this one is very good. So this is some of the internal guts of our socket implementation. The WS field here is the actual WebSocket from Gorilla, and the rest of this stuff is a bunch of kind of supporting objects that let us do what we need to do. And this whole struct is one socket. If you look down here, you'll see when we start up a socket, we put a couple things off into their own routines, reading and writing to the socket. And these channels sort of coordinate. If you want to send a message out to the socket, you'll put a message in this channel, and this guy's just sitting there reading from that and sends it on its way. This project is a one-way communication for the most part. The client doesn't really send anything back to us that we care about, but there are important messages sort of at a lower kind of control level that you still need to worry about with WebSockets. So you do need to consume those. You need to be reading those messages. Those are things like pings. There might be other ones. The ping is the one that I know about. So basically here we're just kind of like consuming those messages, letting them get their pings back. And if the client you close your browser, you'll get an error off of the next read. And that lets us know that we should clean all this stuff up, right? So every time a socket's created, we kind of put these routines out there. If the person leaves the website, we don't want to have those sitting there sucking down memory. And we send a message on the shutdown channel. And the write pump is both reading off of both these channels. When it gets the shutdown, it just returns. So then you're done, and all this stuff kind of goes away. Yeah, I think that's probably all this code is open source, by the way. So you can, if you're more interested, and we can talk, or you can just look at it. But that's kind of the general gist of sort of the internals of the socket. WebSockets have lots of things that they can do for you, but we don't really care about a lot of them. Like I said, it's kind of a one-way communication. So we've kind of trimmed this down to just this interface. So this is the socket interface that one of these S objects would implement. And you were writing, we keep a name associated with these things, which is that's what you see in the URL, that kind of string there. And we want to be able to close them and shut them down. And that's all that this is using. So it's nice to have an interface, and I'll talk a little bit more about why it's nice, but it's nice to have an interface to refer to these things rather than a solid object, because when you're doing testing, sometimes maybe you don't want to have real WebSockets spinning up. You just kind of want to mock what they might be doing and use something else that implements this interface. I'll talk more about that. The other sort of important part of this is keeping track of all the sockets. You have lots of people, maybe multiple people are looking at the same bin, lots of people looking at different bins. And we need to be able to get messages out of Redis, find the right people to send them to. And there's a data structure for that, which is really just a map. But there's a mutex in this map because those things are all happening concurrently. So anytime you add something to the map or remove something, you should really be doing that safely, right? Otherwise you get race conditions, or things aren't where they should be, and things go boom. And that's what this guy does. This is actually kind of a very short file. There's not a whole lot going on here. And then this is kind of putting together both of these guys. So the socket map, and this is actually in the main function of GeoBin. And when we make the binary, this is kind of like, this is what runs. You can see at the top there, we're using a Redis library to set up a client. We're getting a PubSub object out of there, and we're making one of these socket maps. We pass the PubSub in there. The reason we give a PubSub to that guy is because as people are closing their connections, the WebSockets are going away, the socket map is the only one who knows if there's anybody listening to this bin anymore. And if there's not, we don't have to subscribe. We don't have to be listening to Redis anymore either. So the socket map is what actually unsubscribes from PubSub when everybody leaves. And then there's another little concurrent routine that runs and is just PubSubbing and spitting them out into the socket map that finds all the sockets and sends them out. And this is the top level, but like I said, the details are all on GitHub. So yeah, like I said, I was going to talk about interfaces a little bit. If you were here a couple of weeks ago, Francesc from Google was up here, and he gave us a very nice talk about best practices. And one of the ones that he mentioned was this one, that interfaces make testing easier, and that's been my experience. This is just one slide out of his whole deck. There's a lot of other good ones, but I'm going to go into a little bit of detail as to how that was nice for us. Interfaces make testing easier. Hooray! So here's a couple of interfaces that we created to deal with Redis. And naturally, Redis has many other things that you might want to do besides this sort of abbreviated list. But for us, this is all we need. So we just really need an interface that defines those few things. And then when we're writing tests, rather than relying on an actual running instance of Redis to be alongside the tests, we just make an object that satisfies this interface, does basically what Redis would be doing and just exists in memory. The nice thing about that is I'm not testing the Redis client again. Hopefully you've picked a Redis client that has tests, and you can trust that you don't need to retest that stuff. And if you're running something like Travis CI and your tests are running somewhere else, somewhere weird, you don't know, you can't set up dependencies there, this kind of thing allows you to still run all your tests, run your whole code base, just with some other object passed in, So you're not dealing with dependencies, and that's what this is saying. So you can have tests without dependencies, and that's very nice. And this is from some of the test code. It's pretty basic. This is what's implements the Redis interface. So further down in the test file, there's all these methods are defined for this type. And really, though, all it is in the end is a couple maps of the few things that we're storing in Redis, and mutex in case you want to run the tests concurrently. We won't break these data structures, and that's pretty much it. And PubSub doesn't even do anything, right? There's nothing there. So yeah, and the tests for this again on GitHub. Yeah, so it's just really nice to use interfaces for that, and that's it. Josh's going to talk to you about rate limiting.
So our service is rate limited because what it basically is a bucket for you to send post requests into, and we didn't want it to fall down if one person did something wrong and sent way too many requests too fast. And like Ryan said, it's free, and we didn't want it to be sucking up a whole bunch of resources on AWS either. So we did this using Redis and a key up here, and we build the key using rate limit, : and then the URL that you're making a request to, and then the Unix timestamp in seconds. And we used seconds there because that kind of naturally rate limits you by the second. So we're saying 10 requests per second or 100 requests per second, and enforcing that by the key. So we create the key on the second that you make the request, and then we check to see if that key already exists in Redis, and if your request count is greater than the limit. If you have gone over the limit, we return an error and tell you to stop and come back later. Otherwise, we just increment the request count and then continue on with the request. And this logic all ends up going into a very basic middleware, which is just a function that takes a handler func, does some stuff, and then it returns a handler func. So you can do all kinds of things with middleware, like authentication or logging requests, like custom request stuff, more than what you would normally get out of HTTP. So we stuck the rate limiting logic right in there. And then at the bottom, there's an example of creating a router and rate limiting the foo route just by kind of wrapping your handler func with this rate limit middleware. So pretty straightforward. Then deployment process, there's not a whole lot to say here because Go is awesome. We just cross-compile for Linux, AMD 64, tar up the executable with all the static resources, and then we attach it to a release on GitHub that's tagged, and then pitch it up to the server and untar it and kick an upstart script. So it's really nice. One of my favorite things about Go is deploying it, because you really don't have to do much at all. So yeah, that is the end